For most of human history, the idea of empty space felt simple and intuitive. If you removed all matter from a region, no air, no dust, no stars, no light, what remained seemed obvious: nothing, a silent void. This assumption was not careless, it was deeply rooted in everyday experience. When a room is emptied of furniture, it feels empty. When a container is evacuated of air, it feels like nothing is left inside. Classical physics reinforced this intuition by treating space as a neutral backdrop, an inert stage on which matter and energy move, interact, and evolve. Space itself did nothing. It simply existed passively, allowing events to happen within it. This view survived for centuries because it worked remarkably well at human scales. Newtonian mechanics could predict planetary motion with extraordinary accuracy while treating space as absolute and empty. Even when Einstein revolutionized physics with relativity, space was still largely seen as a geometric structure rather than an active physical substance. Relativity taught us that space and time could bend and stretch, but the bending was caused by matter and energy. Remove everything, and you were left with a calm, featureless geometry. Or so it seemed. Quantum physics quietly shattered this picture. Not all at once, but piece by piece, through experimental results that refused to fit classical expectations. One of the most unsettling discoveries was that systems never truly come to rest. Even at absolute zero, where all thermal motion should vanish, quantum systems continue to fluctuate. This behavior is not due to experimental imperfections or hidden variables. It is fundamental. The uncertainty principle ensures that certain pairs of physical quantities cannot both be fixed with perfect precision. As a result, zero energy in the classical sense is forbidden. Nature demands motion, even in its lowest possible state. When this principle is applied to space itself, the consequences are profound. Modern physics describes reality not as a collection of particles floating in emptiness, but as a set of quantum fields that exist everywhere. These fields are not optional. They cannot be removed. An electron is not a tiny bead of matter traveling through space. It is an excitation of an electron field that permeates the entire universe. The same is true for photons, quarks, and every other fundamental particle. Even when no particles are present, the fields remain. The lowest energy state of these fields is what we casually call empty space. But this vacuum state is not empty in any meaningful physical sense. It is an active configuration of fields, governed by precise mathematical rules and filled with restless energy. These fields fluctuate constantly, producing temporary disturbances that rise and fall even when no particles are deliberately introduced. This is not a metaphor. It is a direct consequence of quantum mechanics and has been confirmed by experiment. One of the most counterintuitive aspects of this activity is the appearance of virtual particles. These entities emerge from the energy of the vacuum itself, exist for extremely brief moments, and then disappear. They cannot be captured in the same way as ordinary particles, but their effects can be measured. They influence the behavior of real particles, modify forces, and alter the energy levels of atoms. Their existence reveals that empty space is not static. It is dynamic, reactive, and full of microscopic events. This constant activity means that empty space behaves like a physical system. It has properties that can change depending on conditions. When boundaries are introduced, such as metal plates placed very close together, the vacuum between them behaves differently than the vacuum outside. The allowed fluctuations change, and this difference produces measurable forces. The fact that a force can arise purely from the structure of empty space is one of the clearest demonstrations that space itself is not nothing. The idea that space is an active system also reshapes our understanding of energy. In classical thinking, energy is associated with motion, heat, or fields produced by matter. In quantum physics, energy is woven into the fabric of space itself. Even in the absence of particles, the vacuum has an energy density. This energy is not hypothetical. It contributes to observable effects and may play a role in some of the largest scale phenomena in the universe. One of the most striking implications is the connection between vacuum energy and the expansion of the universe. Observations show that the expansion of the cosmos is accelerating, as if space itself possesses a kind of outward pressure. While the precise explanation remains an open question, many models point to the energy of empty space as a driving factor. If this is correct, then the behavior of the universe over billions of years is influenced by the same restless activity that exists in the tiniest regions of space. This realization forces a philosophical shift as well as a scientific one. The concept of nothingness has always played a powerful role in human thought. Emptiness was seen as the absence of being, the opposite of existence. Quantum physics dissolves this boundary. What we thought of as nothing turns out to be something with structure, behavior, and influence. The vacuum is not a blank slate. It is a living system governed by laws as real as those that govern matter. Importantly, this does not mean that empty space is filled with ordinary stuff in disguise. There are no hidden atoms or undetected particles lurking in the vacuum. The activity arises from the fundamental rules of quantum fields themselves. It is a new category of physical reality, one that does not fit neatly into classical concepts of substance or emptiness. Space is neither a solid nor a fluid, neither matter nor energy in the traditional sense. Yet it acts, responds, and participates in physical processes. The idea that empty space is active also changes how we think about measurement and observation. In classical physics, measuring a system reveals properties that already exist. In quantum physics, measurement interacts with a system that is already fluctuating. The vacuum itself contributes noise, uncertainty, and background effects that cannot be eliminated. Even the most precise experiments must contend with the fact that space itself is never completely still. At extremely small scales, this activity becomes even more intense. As we approach distances where quantum effects dominate gravity, space-time itself is expected to fluctuate violently. Although this regime remains beyond direct experimental reach, theoretical models suggest that space may lose its smooth character entirely. Distances, durations, and even causality may become fuzzy. In this picture, empty space is not just active, it is fundamentally restless at every level. This does not mean that everyday space is unstable or chaotic. On large scales, the fluctuations average out, producing the calm, smooth geometry we experience. A room does not visibly shimmer with quantum activity, and planets do not randomly jump due to vacuum fluctuations. The laws of physics ensure stability at macroscopic scales. But beneath this calm surface lies a sea of activity that never truly stops. Understanding empty space as an active physical system also helps explain why the universe behaves the way it does. Forces, particle interactions, and even the existence of particles themselves depend on the properties of the vacuum. Change the vacuum, and you change the rules of reality. This idea appears in theories where different vacuum states correspond to different physical constants, suggesting that what we call the laws of physics may emerge from the structure of empty space itself. In this light, space is no longer a passive arena but a participant. It shapes interactions, influences outcomes, and carries energy. The phrase, empty space, survives mostly as a convenience of language, not as a literal description. When physicists use it, they are referring to the vacuum state of quantum fields, not to a true absence of physical reality. The deeper we look, the clearer this becomes. Every attempt to isolate nothingness reveals structure instead. Every effort to eliminate activity uncovers more subtle forms of motion. The universe does not allow perfect emptiness, just as it does not allow perfect stillness. The vacuum is the quietest state possible, but quiet does not mean inactive. This understanding represents one of the most radical shifts in modern science. It tells us that reality is fuller than it appears, that absence itself has presence. Empty space is not a void waiting to be filled, it is already full of potential, energy, and law. It is a system with its own dynamics, one that underlies everything we observe. When we say that empty space is not empty but an active physical system, we are not making a poetic claim. We are stating a conclusion forced upon us by experiment, theory, and observation. Space behaves, responds, and contributes. It fluctuates, influences matter, and shapes the universe on every scale. What once seemed like nothing turns out to be one of the most fundamental somethings of all. As this understanding deepens, the idea of space as an active physical system stops being a strange abstraction and starts becoming unavoidable. Once you accept that quantum fields exist everywhere, the vacuum can no longer be treated as a background. It becomes part of the machinery of reality itself. Every particle interaction, every force, every measurable quantity unfolds within this active medium. Space is not merely where physics happens, space is doing physics. One of the most revealing consequences of this is how particles acquire their properties. In modern physics, many characteristics we once thought were intrinsic turn out to be relational, defined by interactions with fields that permeate space. Mass itself, for example, is not simply a fixed attribute of particles. In certain theories, mass arises from how particles interact with underlying fields that fill the vacuum. Remove or alter those fields, and the particles would behave in fundamentally different ways. This means that what we experience as solid, tangible matter is inseparable from the properties of what we used to call empty space. This realization also reframes the concept of stability. If space is constantly fluctuating, why does the world appear so stable? Why don't atoms spontaneously dissolve or objects randomly disintegrate due to vacuum activity? The answer lies in the statistical nature of quantum fluctuations. At small scales, fluctuations are intense and frequent, but they average out over larger distances and longer times. The vacuum is restless, but it is also governed by strict constraints. Its fluctuations are random yet balanced, chaotic yet contained. Stability emerges not because space is inert, but because its activity follows precise rules. This balance becomes especially important when considering the role of the vacuum in fundamental forces. Forces such as electromagnetism are not transmitted through empty space in the classical sense. They arise from interactions mediated by fields that already exist everywhere. When two charged particles repel each other, they are not acting across a void, they are interacting through a field that fills the space between them. The vacuum is not a gap to be crossed, but a medium through which influence flows. At a deeper level, even the concept of a particle traveling through space becomes questionable. In quantum field theory, particles are better understood as localized excitations of fields. They are not independent objects moving through an empty container. They are patterns of energy emerging within an already active system. When a particle appears to move, what is really happening is a shifting pattern of excitation across the field. The vacuum remains continuously active, supporting and shaping that motion. This perspective also helps explain why the vacuum can never be perfectly isolated. No matter how carefully an experiment is designed, vacuum effects always contribute. They influence precision measurements, alter atomic transitions, and impose fundamental limits on what can be known. The vacuum introduces an irreducible background, not due to experimental noise, but because space itself has a minimum level of activity. Even perfect instruments cannot escape it. As physics pushes toward unifying quantum mechanics with gravity, the active nature of empty space becomes even more central. Gravity, unlike other forces, is intimately tied to the geometry of space-time. If space-time itself is subject to quantum fluctuations, then gravity must be as well. This suggests that at the smallest scales, the vacuum is not only filled with fluctuating fields but also with fluctuating geometry. Space may stretch, twist, and ripple in ways that defy classical description. In this regime, the notion of a fixed distance loses meaning. If space fluctuates, then the concept of 2 points being separated by a precise amount becomes uncertain. Length itself becomes a dynamic quantity. Time, too, is affected. The smooth flow we experience may emerge from an underlying jitter at scales too small to observe directly. What feels continuous and orderly could arise from an underlying foam-like structure where certainty dissolves. This idea radically alters how we think about the origin of the universe. If empty space is an active system, then the beginning of the universe may not have emerged from literal nothingness. Instead, it may have arisen from a highly energetic vacuum state. In some models, space itself undergoes transitions, shifting from one vacuum configuration to another. These transitions can release enormous amounts of energy, potentially giving rise to entire universes. In this view, creation is not a sudden appearance from nothing, but a transformation within something that already exists. Even the concept of nothingness becomes problematic under this lens. If space always contains fields and energy, then true nothingness may be physically impossible. There may be no state in which absolutely nothing exists. The universe may forbid it at a fundamental level. The quietest possible state is still active, still structured, still governed by law. What we call the vacuum is not the absence of reality, but the lowest expression of it. This challenges not only physics, but also philosophy. Many philosophical traditions have treated nothingness as a meaningful concept, sometimes even as a foundation for existence. Quantum physics complicates this by showing that the universe does not recognize absolute emptiness. Even absence has presence. Even silence has structure. The vacuum is not the negation of being, it is one of its forms. The active nature of space also reshapes how we interpret causality. If fluctuations are constantly occurring, then cause and effect at small scales become less rigid. Events do not always have clear, deterministic origins. Instead, probabilities govern outcomes, and the vacuum itself contributes to what can happen. This does not mean that the universe is random in a chaotic sense, but it does mean that uncertainty is built into the fabric of reality, not merely a result of ignorance. As experimental techniques improve, physicists continue to probe the properties of the vacuum with increasing precision. Subtle effects, once considered negligible, are now measurable. What was once dismissed as empty background is now a source of valuable information. By studying how the vacuum responds under extreme conditions, scientists hope to uncover deeper laws that govern space, time, and matter. This pursuit highlights an important lesson about scientific progress. Concepts that seem obvious can turn out to be profoundly misleading. Emptiness feels simple only because human perception evolved at scales where vacuum effects are subtle. When we extend our reach beyond those scales, the universe reveals a richer structure than intuition suggests. The active vacuum is a reminder that reality does not owe us simplicity. Understanding space as an active system also fosters humility. It shows that even our most basic assumptions can be overturned. For thousands of years, humans believed that emptiness was trivial. It took modern physics to reveal that what we thought was nothing is, in fact, a complex and essential part of everything. This realization invites caution when making claims about the limits of knowledge. If emptiness itself turned out to be full, what other assumptions might still be waiting to collapse? In practical terms, this understanding has already shaped modern technology. Quantum field effects influence the behavior of semiconductors, lasers, and advanced materials. Vacuum fluctuations set limits on measurement precision and play a role in cutting-edge experiments. What once seemed like philosophical speculation now has tangible consequences in laboratories and devices around the world. Ultimately, the idea that empty space is an active physical system forces us to rethink what it means for something to exist. Existence is no longer limited to tangible objects or visible matter. It includes fields, fluctuations, and structures that cannot be seen directly but can be felt through their effects. Space itself belongs to this category. It exists not as a void, but as a dynamic participant in the unfolding of the universe. The phrase empty space survives mainly because language lags behind understanding. It is a convenient shorthand, not a literal truth. When examined closely, space reveals itself as restless, structured, and indispensable. It supports particles, shapes forces, influences cosmic evolution, and sets the stage for every physical process without ever being empty. In recognizing this, physics delivers one of its most profound insights, that the universe is richer than appearances suggest, and that even what seems absent is deeply present. The vacuum is not nothing, It is the quiet foundation upon which everything stands, humming softly with activity, possibility, and law. When physicists speak about the smallest possible structure of reality, they are not referring to atoms or even subatomic particles. Those ideas already belong to an older layer of understanding. The deeper picture begins at scales so small that the familiar notions of distance, shape, and smoothness begin to break down. At these extreme limits, space itself no longer behaves like a calm, continuous fabric. Instead, it takes on a restless, turbulent character. This is where the concept of quantum foam emerges, not as a poetic metaphor, but as a serious attempt to describe what space is like at the most fundamental level. To understand why this idea is necessary, it helps to remember how physics usually treats space. In everyday life and classical physics, space feels smooth. You can move an object a millimeter, then a micrometer, then even smaller distances in principle, and space seems endlessly divisible. There is no obvious smallest unit of length. This assumption works extremely well for engineering, astronomy, and even atomic physics. But when gravity and quantum mechanics are both taken seriously, this smooth picture begins to fail. Quantum mechanics introduces unavoidable uncertainty. You cannot simultaneously know a particle's position and momentum with perfect precision. As you try to confine something to a smaller and smaller region of space, its energy increases. Gravity, on the other hand, tells us that energy curves space. When these two ideas are combined, a remarkable conclusion follows. If you try to probe space at extremely small distances, the energy required becomes so large that it significantly distorts the space you are trying to measure. At a certain point, the act of measurement itself disrupts the geometry of space. This scale is known as the Planck length, and it represents a boundary beyond which the classical idea of smooth space loses meaning. At distances comparable to this scale, space is no longer a quiet background. It fluctuates violently. Tiny distortions appear and disappear. The geometry itself becomes unstable, constantly changing shape. This dynamic, frothy behavior is what physicists refer to as quantum foam. The word foam captures the idea that space is bubbling with activity, filled with transient structures that form and dissolve almost instantly. Unlike atoms or particles, the features of quantum foam are not stable objects. They do not persist long enough to be directly observed with current technology. Instead, they are fleeting manifestations of quantum uncertainty applied to space-time itself. Tiny regions may momentarily curve, pinch, or stretch. Some theories even suggest that microscopic tunnels or connections between points in space could briefly form before collapsing. Whether these specific features exist remains uncertain, but the broader idea remains robust. At the smallest scales, space is not smooth. This idea marks a profound shift in how reality is structured. It suggests that the smooth space we experience is an emergent phenomenon, much like the smooth surface of the ocean emerges from countless interacting water molecules. From a distance, the ocean looks calm and continuous. Up close, it is turbulent and granular. Similarly, space appears smooth at large scales because the violent fluctuations at tiny scales average out. The calm geometry of everyday experience hides an underlying storm. Quantum foam also challenges the assumption that space-time is fundamental. It raises the possibility that space and time are not basic ingredients of reality, but emergent ones. They may arise from deeper quantum processes that do not resemble space or time at all. In this view, quantum foam is not merely a feature of space-time, it is a sign that space-time itself is dissolving into something more primitive at the smallest scales. One of the most unsettling aspects of this picture is that familiar concepts lose their clarity. Distance becomes ambiguous. If space is constantly fluctuating, then the notion of a fixed separation between 2 points becomes fuzzy. Time, too, may fluctuate, blurring the distinction between before and after. Cause and effect, which rely on a stable temporal order, become harder to define at these scales. Quantum foam does not merely add noise to space, it undermines the very framework we use to describe physical events. Despite its extreme nature, Quantum foam is not a speculative fantasy invented for dramatic effect. It arises naturally when physicists attempt to reconcile the principles of quantum mechanics with gravity. General relativity tells us that space, time is dynamic and responsive to energy. Quantum mechanics tells us that energy cannot be perfectly still. Combine these ideas and a fluctuating space, time becomes unavoidable. Quantum foam is the simplest way to describe the resulting behavior. Although we cannot yet observe quantum foam directly, its implications ripple outward into testable physics. If space-time has a granular structure, then there may be subtle limits to how precisely distances and times can be measured. Over vast distances, tiny fluctuations could accumulate, potentially affecting the propagation of light from distant stars. Researchers have looked for signs of this in astronomical observations, searching for tiny distortions that could hint at an underlying foamy structure. While no definitive evidence has yet been found, the search itself reflects how seriously the idea is taken. Quantum foam also reshapes how we think about the continuity of reality. In classical physics, continuity is assumed. Space flows smoothly and change happens gradually. In a foamy picture, continuity becomes approximate rather than absolute. At sufficiently small scales, reality may be discrete, fragmented into rapidly changing configurations. Smoothness emerges only when these fluctuations are averaged over larger regions. This perspective has deep consequences for the quest to unify physics. Any successful theory of quantum gravity must account for quantum foam. It must explain how space-time behaves when both quantum uncertainty and gravitational curvature are strong. Many candidate theories attempt this in different ways, but they share a common expectation that the smooth space-time of relativity is not fundamental. In some approaches, quantum foam is replaced by more abstract structures. Space-time might be composed of networks, loops, or informational relationships rather than continuous geometry. In others, space-time emerges from entanglement between quantum states. While these ideas differ in detail, they agree on one crucial point. At the smallest scales, space is radically different from our everyday intuition. Quantum foam also forces us to reconsider the meaning of emptiness. If the smallest structure of space is restless and energetic, then emptiness is no longer a passive absence. It is an arena of constant activity. The vacuum is not a blank canvas, it is a seething foundation from which structure emerges. This reinforces the idea that nothingness, as traditionally conceived, has no place in modern physics. There is also a subtle but important implication for determinism. In a foamy space-time, unpredictability is not limited to particles and fields. The geometry itself participates in uncertainty. This means that unpredictability is woven into the very structure of reality. The future is not simply unknown because we lack information. It may be genuinely indeterminate at the most fundamental level. At larger scales, this indeterminacy fades into stability. Planets follow predictable orbits. Clocks tick reliably. Space appears calm, but this calmness is emergent, not fundamental. It arises because the violent fluctuations of quantum foam cancel out when viewed from afar. The universe is stable not because it is still, but because its deepest turbulence averages into order. The idea of quantum foam also reframes the relationship between scale and reality. It reminds us that what is true at one scale may not be true at another. Smoothness, continuity, and even geometry itself may be scale-dependent properties. This is a humbling lesson, suggesting that human intuition, shaped by mid-sized experiences, is poorly suited to judge the ultimate nature of existence. As research continues, quantum foam remains a guiding concept rather than a finished theory. It points toward a deeper layer of reality that has yet to be fully understood. It warns us that familiar concepts will likely need to be abandoned or radically revised, and it provides a bridge between the physics we know and the physics we are still struggling to uncover. In this sense, quantum foam is not just a description of the smallest structure of space. It is a signpost. It tells us that beneath the apparent solidity of the universe lies a restless foundation, one where space itself flickers, fluctuates, and refuses to remain still. It suggests that reality, at its deepest level, is not built on static blocks but on dynamic processes that never fully settle. The smooth space we inhabit is real, but it is not fundamental. It is an emergent calm floating atop a storm of microscopic activity. Quantum foam represents that storm, the endlessly shifting structure from which geometry, stability, and even the notion of space itself arise. As this picture is taken seriously, the role of quantum foam shifts from a speculative idea to a necessary consequence of how nature behaves when pushed to its limits. It becomes less about imagining exotic structures and more about accepting that the tools we use to describe reality have boundaries. Smooth geometry, fixed distances, and continuous time are extraordinarily effective approximations, but they may not survive at the deepest level. Quantum foam represents the breakdown point where approximation gives way to raw behavior. One of the most important implications of quantum foam is that space-time may have a minimum resolution. Just as a digital image looks smooth from afar, but pixelated when zoomed in enough, space-time itself may be composed of fundamental units or processes that cannot be subdivided meaningfully. This does not necessarily mean space is made of tiny blocks in a simple sense, but it does suggest that the idea of infinitely divisible space is no longer valid. Beyond a certain scale, asking for smaller distances may be physically meaningless. This challenges a deeply ingrained assumption in mathematics and physics, that continuity is absolute. Calculus, geometry, and much of classical physics rely on the idea that space and time can be divided endlessly. Quantum foam suggests that continuity may be emergent rather than fundamental. At large scales, the mathematics of smooth curves works perfectly. At the smallest scales, reality may operate according to different rules altogether, rules that do not map cleanly onto classical geometry. Another profound consequence is how quantum foam blurs the distinction between geometry and matter. In classical thinking, geometry describes where things are, while matter describes what things are. In a foamy space-time, this separation weakens. Fluctuations of geometry carry energy, and energy affects geometry in return. Space is no longer a neutral container for matter. It is an active participant that can behave in ways traditionally reserved for physical substances. This becomes especially clear when considering the idea that particles themselves may be inseparable from the structure of space-time. If space at the smallest scales is constantly fluctuating, then particles could emerge as stable patterns within this turbulence. Rather than being objects that exist independently of space, particles may be long-lived excitations or resonances of an underlying foamy structure. This view turns the traditional hierarchy upside down. Instead of space being the stage and particles being the actors, the stage itself may give rise to the actors. Quantum foam also has implications for information. In physics, information is not abstract, it is tied to physical states. If space-time fluctuates at the smallest scales, then the storage and transmission of information are constrained by that behavior. There may be fundamental limits to how much information can be packed into a region of space, or how precisely it can be transferred. These limits are not technological but physical, imposed by the nature of space itself. This idea becomes particularly important when thinking about black holes. Black holes represent extreme cases where gravity and quantum effects collide. The boundaries of black holes, often described as horizons, are places where space-time is stretched to its limits. Many physicists believe that quantum foam plays a crucial role in what happens at these boundaries. The microscopic structure of space may determine how information is preserved or transformed when matter falls into a black hole, addressing puzzles that have challenged physics for decades. The foamy nature of space-time also suggests that the vacuum is not unique. There may be different vacuum configurations, each with its own properties. In such a picture, the universe we inhabit corresponds to one particular arrangement of the vacuum, one stable pattern among many possibilities. Small changes in this underlying structure could lead to drastically different physical laws. This raises the possibility that what we consider fundamental constants are not truly fundamental, but emergent features of a particular vacuum state. This line of thinking naturally extends to cosmology. In the early universe, conditions were extreme, and quantum fluctuations of space-time would have been magnified. Quantum foam may have played a role in seeding the large-scale structure of the cosmos. Tiny fluctuations at microscopic scales could have been stretched by cosmic expansion, eventually influencing the distribution of galaxies and matter. In this sense, the vast structures of the universe may trace their origins back to the smallest fluctuations imaginable. Quantum foam also invites a reconsideration of time itself. In everyday experience, time flows smoothly from past to future. In physics, time is often treated as a continuous parameter, but if space-time fluctuates at the smallest scales, then time may also have a granular or probabilistic character. The clear distinction between moments may dissolve into a haze of overlapping possibilities. The arrow of time, which gives direction to change, may emerge only at larger scales where fluctuations average out. This has philosophical consequences as well. It suggests that the flow of time we experience is not fundamental but emergent. What feels like a steady progression may arise from deeper processes that do not resemble time as we know it. In this view, the universe is not unfolding frame by frame in a smooth sequence, but arising from an underlying quantum process where temporal order is only approximately defined. Despite how radical these ideas sound, it is important to recognize that quantum foam does not imply chaos at observable scales. The universe is remarkably stable. Atoms persist, structures endure. The foam does not tear reality apart. Instead, it provides a foundation upon which stability can emerge. The laws of physics act as constraints that tame the fluctuations, ensuring that large-scale behavior remains predictable even if the smallest scales are wildly uncertain. This interplay between chaos and order is a recurring theme in modern physics. Quantum foam represents the chaotic side of space-time, while classical geometry represents the ordered side. Neither exists alone. Order emerges from chaos through averaging and constraint. The smoothness of space is not a given, it is an achievement, the result of countless fluctuations, canceling one another out. The challenge for physics is to describe this transition mathematically. How does one go from a foamy, fluctuating structure to a smooth, continuous geometry? This is one of the central questions in the search for a theory of quantum gravity. Solving it would not only deepen our understanding of space and time, but also unify the two most successful theories in physics, quantum mechanics and general relativity. Quantum foam also serves as a warning about the limits of visualization. Human intuition evolved to navigate a world of moderate sizes and speeds. It is poorly suited to imagine realities at extremes of scale. Foam, like space, time should not be pictured too literally, as if space were filled with tiny bubbles like soap suds. The term is a guide, not a photograph. The true behavior of space at these scales is likely far stranger than any simple image can convey. Nevertheless, metaphors matter. They shape how scientists think and how ideas develop. Quantum foam provides a way to talk about something that resists direct description. It captures the idea of instability, fluctuation, and emergence in a single phrase. As understanding deepens, the metaphor may evolve or be replaced, but the underlying insight will remain. Another subtle implication of quantum foam is that it places fundamental limits on predictability. If space-time itself fluctuates, then perfect prediction becomes impossible even in principle. This does not undermine science, it defines its scope. Physics becomes a study of probabilities, patterns, and constraints rather than exact outcomes. The universe is lawful, but not rigidly deterministic at every level. This perspective aligns with the broader shift in modern science away from absolute certainty. Quantum foam extends this shift to the very fabric of reality. It tells us that uncertainty is not merely a feature of measurement or ignorance, but a property of existence itself. The ground beneath reality is not solid bedrock, but a restless sea. As experiments and observations continue to improve, physicists hope to find indirect signatures of this foamy structure. These may come from subtle effects in high-energy experiments, precision measurements, or astronomical observations over vast distances. Even a small hint would provide invaluable guidance, narrowing the range of viable theories and bringing us closer to a coherent picture of quantum gravity. Until then, quantum foam remains one of the most compelling ideas at the frontier of physics. It challenges comfort, undermines intuition, and expands imagination. It forces us to accept that space is not what it seems, that smoothness is an illusion born of scale, and that beneath the apparent stillness of the universe lies a foundation of perpetual motion. In the end, quantum foam reshapes our understanding of what it means for space to exist. Space is not an empty arena waiting to be filled. It is a dynamic, fluctuating entity with structure at every level. The smallest scales are not silent or inert, they are alive with activity. From this restless foundation, the stable universe we know emerges, carrying with it the marks of a deeper, stranger reality that continues to challenge our understanding. From the moment quantum theory began to take shape, one idea repeatedly challenged classical intuition, that energy can never be perfectly zero. In everyday thinking, zero energy feels like a natural baseline. A ball resting on the ground has no motion. A cold object eventually reaches stillness. Silence feels like the absence of vibration. Classical physics reinforced this intuition by allowing systems to settle into complete rest. But quantum mechanics overturned this idea at its core. According to its laws, absolute stillness is forbidden. Even when everything appears calm, energy continues to fluctuate beneath the surface. This insight becomes especially striking when applied to what we call empty space. If space truly contained nothing, it should represent the ultimate zero-energy state. No particles, no radiation, no motion. Yet quantum physics insists that such a state cannot exist. The vacuum, defined as the lowest energy configuration of quantum fields, still contains energy. This energy does not sit quietly, it manifests as constant fluctuations that ripple through space at every moment. The source of these fluctuations lies in the uncertainty principle. Certain quantities, such as energy and time, cannot both be fixed with absolute precision. If a system were to have exactly zero energy for an exact amount of time, it would violate this principle. Nature avoids this by allowing small, temporary deviations. Energy can briefly rise and fall, as long as it does so quickly enough. These deviations are not measurement errors or theoretical tricks. They are built into the structure of reality. As a result, the vacuum is never empty in the classical sense. Instead, it becomes a restless environment where energy briefly condenses into particle-like excitations and then dissolves again. These fleeting entities are known as virtual particles. They are not imaginary, nor are they directly observable in isolation, but they have real, measurable effects. They influence how forces behave, how particles interact, and how energy is distributed. Virtual particles constantly appear in pairs, typically as a particle and its corresponding antiparticle. They emerge from the vacuum, exist for an extremely short time, and then annihilate each other, returning their energy to space. This process happens everywhere, continuously. The vacuum is not a passive void but a stage of ceaseless microscopic activity. What makes this idea so counterintuitive is that these fluctuations occur even in the absence of any external disturbance. You do not need to add energy to space to make this happen. The vacuum itself supplies the conditions. This means that empty space carries an intrinsic energy, often called zero-point energy. It represents the minimum energy allowed by quantum laws, not a complete absence of energy. This energy has consequences. It modifies the behavior of particles that move through space. For example, an electron is never truly isolated. It is constantly interacting with the sea of virtual particles surrounding it. These interactions slightly alter the electron's properties, such as its mass and charge. Without accounting for vacuum fluctuations, theoretical predictions would not match experimental results. The agreement between theory and experiment relies on recognizing that empty space is active. One of the most dramatic demonstrations of vacuum energy comes from the behavior of forces. Forces that seem simple at a distance become more complex when examined closely. The strength of certain interactions changes depending on how closely particles approach one another. This variation is not due solely to the particles themselves, but to the influence of virtual particles popping in and out of existence around them. The vacuum effectively screens and reshapes forces, revealing its active role. Another striking consequence is that vacuum fluctuations can produce measurable forces even in the absence of real particles. When two neutral surfaces are placed extremely close together, the pattern of vacuum fluctuations between them changes. Some fluctuations are allowed, others are suppressed. This imbalance creates a force that pushes the surfaces together. The force arises purely from changes in the vacuum's energy. Nothing is added, yet something happens. This challenges the everyday meaning of emptiness. In ordinary language, empty implies inactive and irrelevant. In quantum physics, empty space is energetic and influential. It behaves like a medium with properties that can be altered by boundaries, fields, and geometry. The vacuum responds to conditions, adapts to constraints, and exerts effects that cannot be ignored. The existence of constant energy fluctuations also reshapes how we think about conservation laws. Energy is still conserved overall, but locally and temporarily, it can appear to be violated. Virtual particles borrow energy from the vacuum and return it almost immediately. These short-lived deviations are permitted precisely because they respect the uncertainty principle. Over longer times, energy balances out, preserving conservation at observable scales. This idea can feel unsettling because it blurs the line between existence and non-existence. Virtual particles are not fully real in the same way as stable particles, yet they are not nothing either. They occupy a strange middle ground where they influence reality without becoming permanent features of it. This challenges classical categories and forces us to adopt a more nuanced view of what it means to exist. At a deeper level, vacuum fluctuations suggest that emptiness is unstable. Space does not tolerate perfect neutrality. Given the slightest allowance, it generates activity. This has led some physicists to propose that the universe itself may have originated from a vacuum fluctuation. While such ideas remain speculative, they reflect the recognition that the vacuum is not inert. It is capable, under the right conditions, of giving rise to structure. The constant presence of vacuum energy also raises profound questions about gravity. According to general relativity, energy curves space-time. If empty space contains energy, then it should contribute to the curvature of the universe. In principle, vacuum energy should have an enormous gravitational effect. Yet observations show that its influence is surprisingly small. This mismatch between theoretical expectations and observed reality is one of the deepest puzzles in modern physics. Despite this mystery, there is no doubt that vacuum energy exists. Its effects are seen in precise experiments and in the consistency of quantum theories. The challenge lies not in proving its presence, but in understanding its magnitude and role in the cosmos. The fact that empty space carries energy forces us to confront the limits of our theories and the possibility that something fundamental is still missing from our understanding. Vacuum fluctuations also influence the nature of stability itself. Atoms, for instance, rely on a delicate balance of forces. The vacuum contributes subtle corrections that help stabilize atomic structures. Without these effects, matter might behave very differently. The solidity of everyday objects, in part, rests on the restless activity of empty space. This perspective turns intuition upside down. Stability does not arise from stillness, but from balanced motion. The world is not stable because nothing is happening beneath the surface, but because so much is happening in a way that averages out. The vacuum is noisy, but its noise is structured. It follows rules that produce reliable outcomes at larger scales. The idea of constant energy fluctuations also affects how we think about measurement. No measurement can be perfectly isolated from the vacuum. There is always a background hum of activity that introduces uncertainty. Even the most refined instruments must contend with this fundamental noise. This does not mean measurement is futile. It means there are absolute limits to precision that cannot be overcome by better technology alone. As physics advances, vacuum fluctuations continue to serve as both a tool and a challenge. They are essential for accurate predictions, yet they expose gaps in our theories. They reveal how deeply quantum behavior is woven into the fabric of reality, extending beyond particles and fields into space itself. In this light, empty space becomes one of the most active players in the universe. It supplies energy, mediates interactions, and influences structure at every level. The idea that space could ever be truly empty fades away. Even when stripped of all matter and radiation, space remains alive with fluctuation. This realization carries a philosophical weight. It suggests that absence is not a fundamental category in nature. There is always something happening, even in the quietest possible state. Nothingness, as an absolute concept, may be incompatible with the laws of physics. The universe seems to resist emptiness, filling every gap with potential and motion. Understanding virtual particles and constant energy fluctuations does more than add complexity to physics. It reveals a universe that is intrinsically dynamic. Change is not an exception imposed from outside, it is the default condition. Even the vacuum, the closest thing to nothing that physics allows, is in constant motion. As research continues, these ideas remain central to our understanding of reality. They remind us that the universe is far richer than appearances suggest, and that the deepest truths often lie beneath layers of apparent simplicity. Empty space, once thought to be the absence of everything, turns out to be a reservoir of energy and activity, quietly shaping the behavior of all that exists. As this picture is extended further, the presence of constant energy fluctuations begins to reshape how we think about cause, effect, and even reality itself. If energy is always flickering in and out of existence, then the vacuum is not merely influencing events from the sidelines, it is actively participating in every physical process. Nothing occurs in isolation. Every interaction takes place within and is subtly shaped by this ever-present background of quantum activity. One of the most important consequences of virtual particles is how they blur the boundary between what is considered real and what is considered transient. In classical physics, reality is composed of objects with well-defined properties that persist through time. Virtual particles do not fit neatly into this picture. They cannot be directly detected as individual entities, yet their influence is undeniable. They alter forces, shift energy levels, and leave measurable fingerprints in experiments. Their existence forces us to expand our definition of what it means for something to be physically real. This expanded notion of reality has practical consequences. Calculations in quantum field theory rely heavily on virtual particles to produce accurate results. Without them, predictions would be wildly incorrect. The success of these calculations suggests that the vacuum's activity is not a mathematical convenience, but a reflection of how nature actually behaves. The vacuum contributes to outcomes in a way that cannot be ignored or simplified away. The constant appearance and disappearance of virtual particles also highlights the role of probability in the universe. Events are not always driven by clear, deterministic causes. Instead, they arise from a landscape of possibilities shaped by fluctuating energy. The vacuum provides a reservoir of potential outcomes from which reality selects according to probabilistic rules. This does not mean that anything can happen at any time, but it does mean that the future is not rigidly fixed at the most fundamental level. These fluctuations also help explain why certain symmetries in physics are broken. In theory, many physical laws are symmetric, meaning they treat different states as equivalent. In practice, the vacuum often selects a particular configuration, breaking that symmetry. This process, known as spontaneous symmetry breaking, plays a crucial role in shaping the universe. The properties of particles, the behavior of forces, and even the structure of space-time depend on how the vacuum settles into a specific state amid its fluctuations. In this context, the vacuum is not a passive backdrop, but a decision maker of sorts. It determines which possibilities become stable and which remain fleeting. Small fluctuations can be amplified into lasting features of reality. This is how something structured can emerge from something that appears empty. The vacuum is not merely fluctuating, it is organizing. The influence of vacuum fluctuations extends to the nature of time. Because energy and time are linked through uncertainty, fluctuations in energy imply fluctuations in temporal behavior. On very short timescales, the distinction between before and after becomes less clear. Events overlap, processes blur. Time, like space, becomes a probabilistic concept rather than an absolute one. The smooth flow of time we experience may emerge from this underlying jitter. This idea helps explain why the universe can be both dynamic and stable. At small scales, unpredictability reigns. At larger scales, patterns emerge. The vacuum provides a constant source of variation, while physical laws constrain that variation into stable forms. Order is not imposed from outside, it arises from the interplay between fluctuation and constraint. Vacuum energy also influences the boundaries of what is possible. There are limits to how small, how precise, and how isolated any system can be. These limits are not technological, they are built into the nature of space itself. No matter how advanced our tools become, we cannot eliminate vacuum fluctuations. They represent a fundamental background that cannot be turned off. This has important implications for the future of physics and technology. As experiments push toward greater precision, vacuum effects become increasingly significant. They are no longer negligible corrections, they become dominant factors. Understanding and accounting for these fluctuations is essential for progress at the frontiers of measurement and control. The idea that empty space contains energy also raises questions about the origin of structure in the universe. In the early cosmos, vacuum fluctuations would have been magnified by rapid expansion, leaving imprints that shape the distribution of matter. Tiny, random variations in energy could have grown into the seeds of galaxies and clusters. In this way, the large-scale structure of the universe may be traced back to the smallest, most fleeting fluctuations imaginable. This connection between the microscopic and the cosmic reinforces the idea that the vacuum is a unifying element in physics. It links quantum mechanics and cosmology, the smallest scales and the largest structures. The same principles that govern virtual particles also influence the evolution of the universe as a whole. At a philosophical level, constant energy fluctuations challenge the notion of a static foundation for reality. There is no perfectly still ground upon which everything else rests. The foundation itself is in motion. This suggests that change is not something that happens to the universe. It is something the universe is. Motion, fluctuation, and uncertainty are not disturbances imposed on an otherwise calm reality. They are intrinsic features. This realization can be unsettling because it undermines the search for absolute certainty. If even the vacuum fluctuates, then there is no final layer of reality that is completely fixed. Every level contains motion and possibility. Yet this does not lead to chaos. Instead, it reveals a universe that is resilient, self-regulating, and rich in structure. The vacuum's activity also invites a rethinking of creation and destruction. Virtual particles appear and disappear without violating conservation laws. This shows that creation does not always require a dramatic cause. Small, lawful fluctuations can produce transient existence. The boundary between something and nothing becomes blurred, replaced by a spectrum of degrees of existence. In this framework, empty space becomes a source rather than an absence. It supplies energy, variation, and potential. It is a generator of possibilities that physical laws shape into reality. Matter and radiation are not imposed upon the vacuum from outside, they emerge from within it, shaped by its structure and dynamics. As theoretical and experimental work continues, the role of vacuum fluctuations remains central. They are a reminder that the simplest assumptions often hide the deepest truths. Empty space looks quiet only because its activity operates at scales beyond ordinary perception. Beneath that apparent calm lies a universe in constant motion. In the end, The idea of virtual particles and constant energy fluctuations transforms our understanding of emptiness. The vacuum is not a void waiting to be filled. It is already full, already active, already participating in every process. What we once called nothing turns out to be a restless sea of energy, quietly shaping the past, present, and future of the universe. For most of human history, nothingness felt like a simple concept. To say that something was nothing meant that it had no properties, no behavior, no influence. Empty space was imagined as the ultimate example of this idea, a void that merely existed so that objects could occupy it. This intuition shaped philosophy, language, and science for centuries. But quantum physics quietly dismantled this idea, revealing that what we call nothing is not simple at all. It is structured, active, and deeply influential. The discovery that the vacuum has properties forces us to abandon the notion that emptiness is the absence of reality. In quantum theory, empty space is defined not by what is missing, but by what remains when everything removable is taken away. What remains are quantum fields in their lowest energy state. These fields do not disappear when particles are removed. They persist everywhere, forming a continuous foundation for reality. Their presence alone is enough to give empty space physical character. This realization changes how we understand nothingness at a fundamental level. Nothing is no longer the opposite of something. Instead, it becomes a special state of something, a condition of minimal energy rather than total absence. Empty space is not blank, it is organized. It follows laws, responds to boundaries, and interacts with matter. It has an internal structure that cannot be stripped away. One of the most profound consequences of this shift is that empty space can influence events without containing any matter. The behavior of particles, forces, and even light is affected by the properties of the vacuum they move through. This influence is subtle but real. It shows that space itself participates in physical processes rather than merely hosting them. This new view also dissolves the sharp boundary between existence and non-existence. In classical thinking, something either exists or it does not. Quantum physics introduces a spectrum. Virtual particles, fluctuations, and transient states occupy a gray zone where influence does not require permanence. Empty space is full of such transient activity. It continuously gives rise to effects that matter cannot produce on its own. The idea that nothingness has structure challenges our instinctive reliance on common sense. Human intuition evolved in an environment where quantum effects are hidden. At everyday scales, empty space feels inert because its activity averages out, but when examined closely, that apparent stillness reveals itself as the result of countless interactions canceling one another. Calm emerges from motion, not from the absence of it. This insight also reshapes philosophical questions about origins. Traditionally, creation has been imagined as something arising from nothing. Quantum physics suggests a different picture. If empty space already contains energy and structure, then creation may involve rearrangement rather than emergence from absolute nothingness. The vacuum becomes a fertile ground, not a barren void. Importantly, this does not trivialize the concept of creation or change. Instead, it makes them more subtle. Change does not require a dramatic beginning from emptiness. It can arise from fluctuations within an already active foundation. This aligns with the idea that the universe is not built upon nothing, but upon a minimal state of being that cannot be reduced further. The recognition that empty space has properties also affects how we think about limits. There is no ultimate baseline of zero influence. Even when everything else is removed, space still matters. This sets fundamental limits on isolation, precision, and control. No system can be completely detached from the vacuum because the vacuum is always present. This view carries a deeper lesson about knowledge itself. Concepts that feel absolute often turn out to be approximations. Nothingness seemed absolute only because we lacked the tools to probe it. Once those tools became available, nothingness revealed complexity. This suggests that other seemingly simple ideas may also conceal hidden depth. Empty space, once dismissed as irrelevant, now stands at the center of modern physics. It shapes interactions, stores energy, and influences the evolution of the universe. It is not a passive background but an active participant. The phrase, empty space, survives more as a linguistic habit than as an accurate description. By redefining nothingness, quantum physics invites a more nuanced view of reality. Existence is not limited to solid objects and visible motion. It includes fields, fluctuations, and latent energy. Reality extends into regions that cannot be seen directly, but can be felt through their effects. In this light, nothingness loses its simplicity but gains significance. It becomes a subtle and essential aspect of the universe rather than an absence to be ignored. Empty space is not empty of meaning, influence, or structure. It is one of the deepest expressions of how the universe organizes itself. Understanding this does more than correct a scientific misconception. It reshapes how we think about absence, silence, and emptiness in every context. What appears empty may be full in ways that are not immediately obvious. The universe teaches us that nothing is rarely truly nothing, and that the quietest states often hide the most profound activity beneath their surface. The relationship between quantum foam and space-time forces a fundamental rethinking of what space and time actually are. For centuries, they were treated as separate, stable frameworks, space as the container of objects and time as the flow in which events unfold. Even when Einstein unified them into space-time, the underlying assumption of smoothness remained. Space-time could bend and stretch, but it was still continuous, predictable, and well-defined at every point. Quantum foam disrupts this picture at its foundation. When quantum effects are applied to space-time itself, the smooth fabric described by relativity begins to unravel at extremely small scales. Space and time are no longer passive coordinates. They fluctuate just like energy and matter do. These fluctuations are not disturbances imposed from outside. They arise from the same uncertainty principles that govern all quantum systems. The result is a version of space-time that is restless and dynamic even in the absence of matter. This restless behavior suggests that space-time is not fundamental in the way it appears. Instead, it may be an emergent phenomenon, arising from deeper quantum processes. Just as temperature emerges from the collective motion of molecules, the smooth geometry of space-time may emerge from the collective behavior of quantum fluctuations at microscopic scales. Quantum foam represents this underlying level, where the familiar structure of space-time dissolves into something more primitive. In this regime, traditional notions such as distance and duration lose their sharp meaning. If space is constantly fluctuating, the idea of a fixed distance between 2 points becomes ambiguous. Similarly, if time is subject to quantum uncertainty, the distinction between precise moments blurs. Events no longer sit neatly on a smooth timeline. Instead, they are embedded in a probabilistic structure where exact ordering may not always be well defined. This has profound implications for causality. In classical physics, cause precedes effect in a clear, orderly sequence. In a foamy space-time, this sequence becomes fuzzy at the smallest scales. While causality remains intact at macroscopic scales, it may break down or become probabilistic at microscopic ones. This does not mean that the universe is chaotic, but it does mean that order is an emergent property rather than a fundamental guarantee. Quantum foam also implies that space-time has a kind of texture. It is not infinitely divisible. There may be a smallest meaningful unit of length and time, beyond which the concepts themselves cease to apply. This idea challenges centuries of mathematical tradition, but aligns naturally with the limits imposed by quantum gravity. At scales where quantum foam dominates, asking what lies between 2 points may no longer make sense. The interaction between quantum foam and gravity is especially important. Gravity is unique among forces because it is a manifestation of space-time geometry itself. If that geometry fluctuates, then gravity must also fluctuate. This suggests that gravitational effects at very small scales are inherently quantum in nature. Understanding this relationship is one of the central challenges of modern theoretical physics. The influence of quantum foam may also extend to extreme cosmic environments. near black holes, or during the earliest moments of the universe, space-time is subjected to enormous energies. In such conditions, the foamy structure of space-time could become more pronounced, influencing how matter behaves and how information is processed. These environments may offer indirect windows into the nature of quantum foam. Another implication is that space-time may not exist independently of observation and interaction. If its structure is defined by quantum processes, then it may only take on definite form when averaged over many interactions. This reinforces the idea that the classical world is not a direct reflection of fundamental reality, but a statistical outcome of deeper processes. The relationship between quantum foam and space-time also highlights the limits of visualization. It is tempting to imagine tiny bubbles or ripples in space, but such images are only approximations. The true nature of these fluctuations likely defies simple pictures. They may involve changes in connectivity, topology, or relationships that have no classical analog. Despite this complexity, the emergence of smooth space-time from quantum foam is one of the most hopeful ideas in physics. It suggests that order can arise naturally from underlying chaos. The stability of the universe does not require a perfectly rigid foundation. It can emerge from a dynamic, fluctuating substrate governed by consistent rules. This perspective changes how we think about the universe's structure. Space-time is not a static arena, but a living framework, shaped and reshaped by quantum activity. Its apparent calmness is a large-scale illusion produced by averaging over immense numbers of fluctuations. Understanding the connection between quantum foam and space-time is essential for any complete theory of reality. It represents the meeting point of quantum mechanics and relativity, two theories that have revolutionized physics yet remain incomplete when taken alone. Quantum foam offers a glimpse of the deeper layer where these theories may finally converge. In this view, space and time are not eternal, unchanging backdrops. They are emergent, dynamic aspects of a universe that is active at every scale. The quantum foam is not a curiosity at the edge of physics, it is a clue to the true nature of space-time itself, revealing that even the fabric of reality is shaped by uncertainty, motion, and change. For a long time, the idea that empty space could produce measurable effects seemed almost philosophical rather than scientific. If nothing is there, how could it do anything? Yet modern experiments have repeatedly shown that the vacuum is not only real but observable. Its influence can be measured with extraordinary precision, and these measurements leave little room for doubt. Empty space is not an abstract concept, it is an active physical entity whose effects appear in laboratories and observations around the world. One of the clearest ways the vacuum reveals itself is through how it affects matter at very small scales. When atoms are examined with high precision, their energy levels do not behave exactly as classical or even simple quantum models would predict. There are tiny shifts in these levels that cannot be explained by the atoms alone. These shifts arise because electrons are constantly interacting with vacuum fluctuations. The surrounding space is alive with virtual particles that subtly alter how electrons move and how they bind to the nucleus. The agreement between theoretical predictions and experimental results depends on including these vacuum effects. Another striking example comes from forces that appear where none should exist. When two neutral, uncharged objects are brought extremely close together in a vacuum, they can experience an attraction. This force does not arise from magnetism, electricity, or any classical interaction. It emerges because the presence of the objects changes the structure of vacuum fluctuations between them. Some modes of fluctuation are suppressed, others remain allowed, and this imbalance produces a measurable force. The effect is small but undeniable, and it has been confirmed in multiple experiments. The existence of such forces demonstrates that empty space responds to boundaries. It behaves differently depending on geometry and conditions. This is not how nothing is supposed to behave. A true void would remain indifferent to what surrounds it. The vacuum, by contrast, adapts and reacts, revealing its physical nature. Vacuum effects are also observed in the behavior of light. When light travels through empty space, it does not simply move through a passive medium. The vacuum can influence how light propagates, especially in the presence of strong fields. Under extreme conditions, light can even interact with light through vacuum processes, something that would be impossible in a truly empty void. These effects are subtle, but they are predicted by theory and supported by experiment. Even the properties of fundamental particles provide evidence of the vacuum's activity. The measured values of particle masses and charges are not simply intrinsic numbers. They are influenced by interactions with vacuum fluctuations. A particle surrounded by the vacuum is not the same as a hypothetical particle in perfect emptiness, because perfect emptiness does not exist. The vacuum dresses particles with a cloud of virtual activity that modifies their behavior. At larger scales, the influence of empty space becomes even more dramatic. Observations of the universe show that its expansion is accelerating, as if space itself contains energy that drives this expansion. While the precise nature of this energy remains an open question, it is closely related to the idea that the vacuum has an energy density. This suggests that empty space plays a role not only in microscopic experiments but in the evolution of the entire cosmos. These observations force scientists to take the vacuum seriously as a component of physical theory. It is not an optional add-on or a mathematical trick. Removing it would break the connection between theory and experiment. The vacuum contributes real effects that must be accounted for to understand reality accurately. Importantly, these experimental confirmations do not rely on a single line of evidence. They come from atomic physics, particle physics, optics, and cosmology. Each field, working independently, encounters phenomena that point to the same conclusion: empty space is active. This convergence of evidence strengthens the case beyond reasonable doubt. The ability to observe vacuum effects also sets fundamental limits on what can be measured. No experiment can ever be perfectly isolated from the vacuum. There is always a background of fluctuations that introduces noise and uncertainty. These limits are not due to technical imperfections, but to the nature of space itself. Even ideal instruments would face them. This realization changes how scientists think about precision and control. It highlights that there are boundaries to knowledge imposed not by ignorance, but by the structure of reality. Understanding the vacuum helps define these boundaries and shows where classical expectations fail. The fact that empty space has observable effects also influences technological development. As devices become smaller and more sensitive, vacuum fluctuations become increasingly relevant. They must be considered in the design and interpretation of experiments and technologies operating at the quantum scale. Taken together, these observations erase any remaining distinction between empty space and physical substance. The vacuum may not be matter, but it behaves in ways that matter does. It stores energy, responds to conditions, and influences interactions. It is measurable, testable, and essential. The idea that nothing can do something is no longer paradoxical. It is a statement about how reality works at its deepest level. Empty space is not an absence but a subtle presence, woven into every experiment and observation. Through its observable effects, the vacuum reveals itself as one of the most important components of the universe, quietly shaping phenomena from the smallest particles to the largest cosmic structures. The realization that true emptiness does not exist marks one of the most profound shifts in modern scientific thought. For centuries, emptiness was treated as a default state, a background against which reality unfolded. Space was imagined as a passive void, waiting to be filled by matter and energy. This idea felt natural because it aligned with everyday experience and classical intuition. Yet as physics progressed, this assumption quietly collapsed. What replaced it was not a new version of emptiness, but the understanding that the universe does not permit absolute nothingness at all. In modern physics, every region of space is filled with quantum fields. These fields are not optional additions to reality, they are fundamental. They exist everywhere and cannot be removed. Even when no particles are present, the fields remain in their lowest energy state. This state, often called the vacuum, is the closest approximation to emptiness that nature allows. But it is not empty in any classical sense. It is structured, active, and governed by precise laws. This means that the idea of a region of space containing nothing at all is physically meaningless. There is no switch that can turn off the fields. There is no way to strip space down to pure absence. Even the quietest vacuum is alive with fluctuations, energy, and potential. The universe resists nothingness. It always retains something. This insight reshapes how we think about existence itself. Existence is no longer limited to objects that can be seen, touched, or directly detected. It includes underlying structures that manifest only through their effects. Empty space, once dismissed as irrelevant, becomes a foundational element of reality. It influences particles, forces, and the evolution of the cosmos. The disappearance of true emptiness also affects how we understand beginnings and endings. If there is no absolute nothing, then creation is not the sudden appearance of something from nothing. Instead, it is a transformation of existing structure. The universe may evolve, change state, or reorganize, but it does not emerge from a literal void. This perspective alters both scientific and philosophical discussions about origins. Similarly, destruction does not lead to nothingness. When matter and energy are removed from a region, what remains is not emptiness but the vacuum, still governed by laws and still capable of influencing outcomes. Absence becomes a relative concept rather than an absolute one. This view also clarifies why the laws of physics appear so universal. Because the vacuum exists everywhere and carries the same underlying structure, the behavior of particles and forces remains consistent across the universe. The uniformity of physical laws is tied to the fact that there is no true empty space where different rules might apply. The vacuum provides a common foundation. The non-existence of true emptiness also places limits on human imagination. Many intuitive concepts rely on the idea of absence as a baseline. Quantum physics shows that such baselines may not exist. Reality does not begin from zero, it begins from a minimum state that is still active. This challenges the way language and thought have been shaped over centuries. Importantly, this does not mean that nothing is a useless concept. It remains meaningful in everyday contexts and approximate descriptions. But at the deepest physical level, it is an approximation, not a fundamental truth. When pushed to extremes, the concept breaks down. The realization that true emptiness does not exist also reinforces the interconnectedness of reality. Nothing is isolated. Every region of space is linked through the presence of shared fields. Events in one place can be influenced by the structure of the vacuum that extends everywhere. The universe is not a collection of disconnected objects floating in nothing. It is a continuous system with no gaps. This understanding invites humility. It reminds us that intuition, shaped by limited experience, is not a reliable guide to ultimate reality. What feels obvious can be deeply wrong. Emptiness seemed simple only because we could not see its structure. Once we learned how to look, simplicity gave way to complexity. The absence of true emptiness also carries a subtle sense of permanence. While objects may come and go, the underlying fabric of reality remains. Fields fluctuate, configurations change, but the vacuum persists. This does not imply timelessness or immutability, but it does suggest that reality always retains a foundation, no matter how much transformation occurs. In this sense, the universe is never truly silent. Even in its quietest state, it hums with activity. This hum is not noise in the ordinary sense, but the expression of fundamental laws at work. It is the background against which all phenomena arise. Understanding that true emptiness does not exist completes the shift begun by quantum physics. It replaces the idea of a universe built on nothing with a universe built on structure, energy, and law at every level. Empty space becomes a misleading phrase, a relic of older thinking. The deeper message is not merely scientific but conceptual. Reality is richer than absence allows. The universe does not rest on a void, it rests on a dynamic foundation that never fully disappears. Even when everything else is gone, something remains. That something is not matter or light, but the quiet, persistent activity of space itself. In accepting this, physics arrives at a humbling conclusion. There is no absolute nothing to fall back on. There is only the universe in different states of activity. Emptiness, once thought to be the simplest idea of all, turns out to be one of the most complex. And in that complexity lies a deeper understanding of why the universe exists as it does, full rather than empty, active rather than silent, something rather than nothing.